I think we're good. Hello, everyone. My name is Alex Rodriguez, and on behalf of the School of Architecture, I give a warm welcome to whoever is watching us from Facebook Live and everyone present here today. For Ibero Tijuana, it is with great pleasure to have our invitee today, Eduardo Martino, who is here with a presentation titled Lessons Learned from Being a Quantum Architect. We would like to thank you for taking the time to be here and hope you well on your virtual stay in Tijuana. Eduardo is a materials and nanotech engineer from EPFL in Lausanne, with a background in management of innovation. With expertise in the understanding of optical, electrical, and structural properties of complex materials for electronics and energy applications, he has developed new scientific methods and built fully automated measurement devices. He has had the opportunity to learn how new materials are created and what defines them, and in 2020, received the EPFL Physics Doctoral Thesis Award. For his thesis, Electrons Leave the Flatland, Out-of-Plane Charge Dynamics in Layered Materials. We invite all of our guests to keep their cameras and microphones off for the duration of the presentation. At the end of the presentation, we will open a Q&A session. If you please, you can write your questions in the chat. And without further ado, Eduardo, the room is all yours.
Thanks, Alex. Thanks a lot very much for inviting me and giving the opportunity to be here and give this presentation. So the title might seem a bit peculiar, being a quantum architect, but my desire with this presentation is to give you my overview of a path, and in particular, the challenges that comes when you want to create and innovate. And this, I think, is something that we all share in our daily projects and tasks. You will see some of the topics in here, you might feel far, but they will actually be very close to you in your everyday activity. Now, let me start first by introducing better myself. I'm Italian, first of all, and I can say that I'm both an engineer and a scientist. I'm currently located in Zurich, where I work for Hitachi Energy as a scientist in our corporate research center. And if I have to summarize my professional path, I've been throughout technological innovation. My desire is to learn how to create with materials, in particular for electronics and energy application. And it's throughout this path that I had this opportunity to combine these three different aspects of science, technology, and innovation throughout both my education and my professional experiences that in particular went through different academic institutes. My engineering background from Italy, from the two Politecnico of Milan and Turin, my science background from the Federal Institute of Technology in Lausanne, working in the laboratory for physics of complex matter, and the innovation part that followed throughout this path. And it's really also where I had the opportunity to work in Delta Scuola Politecnica in an interdisciplinary project that took together engineer, architects, and designer to work together on complex aspects of innovation. And with that introduction, now let me start with a bit our path on how design and create with atoms. What you will see here is, again, is a general concept. This is not meant to be neither a physics lecture nor really an architectural presentation, but it's a path that I want to share with you on creation and innovation. First of all, when we create with atoms, it's an interesting game that we play between symmetry and combination of atoms. And the symmetry is a very nice concept that nature knows how to use very well. And it's also a way that it is used to distinguish meaning and creation. A very classic example is what nature can do with the same type of atom, the constituent of everything around us. In this case, with carbon. And by changing their position, it can either be graphite or it can be diamond. And what we do with our job as creator with atoms, we can provide nature with the right ingredients and conditions that it will give us a material that we want. Now, as a scientist or as an engineer, also this creation of material has a very specific meaning, right? It's basically writing. And it's based by combining symmetries, and they're not endless symmetry. Nature provides us with 14 possible combinations of symmetry and atoms, basically the word that goes in this sentence made by symmetry, that we can use around 90 of them. And it's by combining them that we can create materials and new properties. Now, this combination actually cannot have endless phases. There are very clearly described, there are 230 possibilities. And what you see here in this table is a summary of all these possible symmetry and combination. These are basically the building block, the building sentences that you can use to create with matter. All of this seems kind of a very exotic thing, but I can show you immediately that in there, there's something you might be very familiar with. If you take a line in there that is characterized by their symmetry, you might find something that might look far, but is a name that might remind you something. And Portlandite is this material with these very specific atoms and symmetry is a key constituent of concrete. Now, with that in mind, what is also we learn how to create is how to combine these two, how to move from symmetry and creation. And I think, again, a very interesting example is to play between graphite and diamond, how we understood to turn one into the other by pressure, by moving the atom closer together and to have this transformation. These have been indeed some of the projects that I had where I took care of transforming a materials that looks like graphite, this differed for its color, for this bright red. And when you force the atom to move closer together, we suddenly change the symmetry we like to leave and assume different properties. This is indeed something that I had the opportunity to create and study with this specific experiment that is actually located in Paris. But you might ask now, why? Why would you want to do that? What's the point of changing and creating a position of atoms? Well, that's the creation of a new material. And you might want to do that for different reasons. You might want to create a new material for a structural reason. You want to create something solid that you can sit on top. Or you want to use something that is more of an intrinsic property of that material. And this is indeed where my research has been focused. The use and the control of the properties inside material. And most of all, one in particular, which is called charge dynamics. Charge dynamics, it's a phenomena that happen everywhere around us. This picture is an example. Charge dynamics is the consequence of the fact that in nature is created by atoms, as in there you have these two elements, the nucleus and the electrons, that both have a charge. And dynamics just means that one of them is moving away from the other and create this flow of electricity. It can happen in the atmosphere, it happens inside of you in any moment. Your neurons working as charge dynamics happening. A photosynthesis in a plant is charge dynamics happening. But where I'm interested is this phenomena happening inside the material. And we started understanding how to use that as a mankind a few years after the French Revolution, when Alessandro Volta created a battery. And the battery is a very interesting tool because allow us to create this very intrinsic clockwork of nature of electricity moving and make it take any possible path between the two poles of the battery. And that concept, we use it today to power countless devices and to really make everything work. But the question there now is, how does electricity move inside a wire, right? And this is where I want to take you. This is now where we're going to enter in the world of quantum physics, and where now the design, the architecture of the atom and the quantum properties inside of them becomes relevant. Now, wire is something you're super familiar, right? You take the charger of your phone, you plug it on the socket in the wall, and you charge your computer, and electricity flows through it. But how, right? That wire is made of a material which means has a very specific constitution of symmetry and atom. The symmetry is well defined, the atom is mostly copper, and the electricity will flow inside of it. Now, think for a moment, how would that happen? This is something very solid, and that yet you have something flowing inside. Is that going to be something like this? Is that going to be like a flipper of ball that transports electricity that bounce off in this very compact space? Well, the reality is now here we enter in the world of quantum dynamics, which is far from what we ever experienced in our life. And what I can simplify is what we see there is surf, basically, is your charge, the electricity flowing to the material, blend into the symmetry of the atoms inside the wire. And it follows a pattern of a wave as it progresses through the wire. Now, keep in mind this concept of waves and electricity flowing to the symmetry, because we will see now how we go from that to something that is very close to you. This path is something that can take any trajectory in any material and has been indeed be the focus of my research. But it's also what distinguishes something that transports electricity, like a wire, and something that doesn't. And the concept, you just have to imagine the same. In one case, you have this wave that follows the symmetry of the atom. In the other case, you have all the ingredients to transport it, but it just doesn't happen. And now with the knowledge of science, what we managed to understand is what makes that happen. How we can have wave, how we cannot have them, how we can have electricity flowing, how not having electricity flowing, how we can turn it on and off, have a switch, 1 and 0. And from there, you know that if you go on and off 1 and 0, you made a switch. That could be a very interesting conceptual thing, but many years ago, someone understood that you can do that with a single material, and that was a great discovery that made it possible a lot of application. That was the creation of the first transistor. Using a well-defined set of atoms with a symmetry that is the same as diamond, but now the word is different. This is not anymore carbon, this is not diamond. In their case was germanium, and what you can use today is silicon. And do start with silicon, you might be familiar because this concept of going on and off of this flow of electricity in silicon is the basic for all computers around you. And so this is an example how the understanding of the quantum physics inside the material took us such a long way from a very basic concept to the creation of a device that we use every day. And from that, there are also other applications that I think they're even coming now, they're even more interesting. For example, one that I'm really looking for my projects is how to use this property to transport incredible amount of power, sufficient to power 3.6 million households more than 600 kilometers away. These are a bit the basic to give you an idea of what we can do now when we have control of atoms and their symmetry and their properties. But what are the new frontiers? Now, the transistor, as I said, it's old, right? It came right after the Second World War, but today had such a huge impact. Now, what is the new stuff today that will have a huge impact in the future? And there are a few, you might have heard them. Maybe the first one is nanotechnology, which is actually something that started being said around the 90s. And today, the hotter topic is more quantum materials. And if you're closer to basic research, what is even coming after that is called topological state of matter or defects. Now, the difference between them in nanomaterials, these atoms and symmetry, you go smaller and smaller in scale. Now you're taking close to a single atom domain. When you look for the quantum properties, now that wave that ride around the symmetry, you use them. You try to harness that specific way to really do what you want. And the last one I think is interesting is really you take advantage of the defects in the symmetry to make something new. But what are those? You might understand, and oftentimes you might have seen maybe for nanomaterials that are really the future, they're going to make something new. Well, I spent a lot of time in this field and I came to this conclusion. All these three, they have something in common. And what I have in common is that they are tools. And as a tool, you can imagine that they're just as good as the problem they can help you to solve. There's not a tool that will make you fix everything. And there's also a tool that have a good way to be used and a wrong one. But what they can offer as tool is to help us create innovation. But not because you have something new to make innovation, but because innovation happens by combining existing knowledge. And so we have these competences, these new tools that are appearing, which are now becoming a base and a tool where we can construct innovation around them. Because when you innovate, you use something that already exists. It becomes something groundbreaking when the soil around that seed becomes fertile. When now combining this tool creates something that is really have an impact. Now let me instead go back a bit to this example and show you really what are the most fascinating frontiers that we have today in creation. First of all, with nanomaterials. Nanomaterials, as I said, is going small in dimension. So small that to give you an idea, 1 nanometer is the same difference in scale from a meter as the size of an orange with respect to this planet, right? So if you play with 1 nanometer, it's basically going the same scale from the whole planet to an orange. And this is what you can see here. You can actually find for yourself on YouTube. is the ultimate example on how far we got in controlling precision materials down to a single atom. What you see here is not a sketchy drawings. It's not something simple. Each of these dots is a single atom. And what the scientists at IBM that did this video could do was really place one by one each atom with so much precision they could make a video. That's the ultimate frontier of nanotechnology. That's the ultimate level of control that we have all dreamed since we started imagining as mankind that matter is made of atoms. But in your daily life, where are you gonna see that? Where are you gonna see the impact of nanotechnology? And I give you an example, and you can find in something like this, in a church. Let me give you more in detail why nanomaterials can be found here. Because now you start playing with materials and you go smaller in their dimensions. And doing so, you start playing a bit with them, you start making them behave differently. And the classic example where they were used before the concept of nanotechnology could be used was for glass staining. I'm talking about glass that is colored inside of it, right? It's not painted. And typically, this could be the red color. In there, inside that glass, there are nanoparticles of gold. And because of the smaller dimension of this group of atoms now, they're changing color. And what you find even interesting is, if you look at the last example, you have particles that have a similar dimension, but now the geometry is different, and that also plays a role. And so we started using this tool of nanotechnology as mankind, actually a few centuries ago. We started now completely understanding it as from a scientific perspective only recently. Now let me go to something that I think today is a bit more the hot topic, is quantum materials, the using of the quantum properties of materials to create something. What you see here is a bit the topic that is becoming hot, which is quantum computing. It's using these quantum properties with so much precision that you can make computation, right? Basically, this is a gigantic fridge. The computer is where the two scientists are handling the device, and it's used to make a different kind of operation. I introduced you to the transistor, which is this on and off, 1 and 0. The quantum computer instead takes this to another level. It doesn't do on and off. It takes the superposition of this wave of the quantum state of 1s and 0. And because of that, for certain specific calculation, it could actually be extremely more powerful. And this is a new frontier now. But as we see it for nanotechnology, where can we see this in our everyday life? This is an interesting example because it's something that you can find close to you very soon. And it's this case. Now, you might be familiar with this object and you might recognize who designed it. Where is nanotechnology and quantum science? Because both of them are in here. Now, that is made of stainless steel. Now, think it for a moment. It's stainless. It doesn't rust. Now, why is that? Because if you check material that cannot rust, it's only gold, platinum, iridium. That is not made of these materials. It doesn't rust for a very reason linked to nanotechnology. That pot covers itself with a few nanometer thin protective layer of another material that is not stainless steel, is an oxide of chromium. And what it makes it interesting, it's a nanomaterial that grows on top, and if you scratch it, it grows back again. And now, why this is protected? A reason why objects rust and corrode is because electricity moves inside them, right? This phenomenon of charge dynamics is actually the same reason why metal turns into rust. And the reason why it doesn't here is so much related to quantum physics. What happened there, this movement of electricity, this wave, they kind of jump together and they cannot move anymore. It's really the extreme of the quantum physics now. All these waves, they kind of instead interlock into each other. And it's basically the same as seeing a quantum or a quantum traffic jam. And that's the reason why a stainless steel, it is actually stainless. It's something that you might see every day around you. And the last one, I think it's another example of topological state of matter. As I said, is the latest interest in science. So I wouldn't say that today we have a clear vision of how to use it. But as technology, we use that for quite a lot of time. It's actually what the blacksmith and his assistant are doing now. Hammering this piece of metal, what they do is they break the symmetry of the atom. They introduce defects. What you see is this very precise building, and every hit with a hammer just push part of the atom in one direction while others cannot follow after. And it creates this point where basically it's like a zip connecting together where there should be atoms, but they cannot fit together. That is a topological defect. And that's the reason why steel, after you hammer it, becomes stronger. And you can even see that by yourself. Each dot here, it's a single atom. And this is a very interesting technology that now we can only understand, but again, it's a few centuries old. What I want to take you from here is a bit the path to see this discovery. What I show you is how this concept of nanomaterial, quantum properties, they're so much close to us. But how did we get there with understanding? Because one thing is to use it as a technology, is to use them to create something. Another one is the science to understand them. And the reason for understanding things is once you know how they behave is when you really start having additional control. You can do what you want. So oftentimes, what I realize is we start using things before we understand them, right? You buy your new phone, you unbox it to start using. You don't ask yourself, how does it work? That's how we did as mankind with many technology. We started using them before we could understand them. Now, once you understand fully something, you can do much more, right? Ideally, if you fully understand your phone, you could produce it by yourself if you would have the complete set of knowledge. Or if you have the complete set of knowledge of the atomic structure of material and their quantum properties, is where you can start creating something new. And that's the path that I took. And what I want to take with you is, again, let's try to take this path together for one of the examples we have seen. Let's try to take it for this object. I think it's the most common example that we have around us, and is the one that has both nanomaterials and quantum properties together. How will we do that? How will we take that path to discover these properties together? Because we have to see something extremely small. We have to understand that it's made of something that is not what we bought. You buy something of stainless steel, and now you have to look for something that is not that. And then you have to understand some magical reason, basically, why electricity is supposed to move there, but it doesn't, for the intrinsic nature of quantum properties in these materials. So let's try to take this one by one, and let's take this path, which is kind of what my research has been about. So let's do this together. Step one, I want to see something that is 1/9 times 0 of a meter, right? Something that is extremely small. So first of all, you're not going to see it. And if you want to explore it, a basic rule is the smaller is the things you want to look for, the bigger will be the tool and the microscope that you're going to use. So if you want to see that, well, you're going to use something like this. There's not anymore a desktop experiment. I mean, when you buy this microscope, you get the table where it's mounted together. And with this, you can start seeing the atoms. So we might find answer to our first question. And now the second one, what is this new super thin protective layer around this material made of? And for that, you need an entire city, basically. What you see here is a research center, one of the most advanced here in Europe, that is located in the Alps in France, close to Grenoble. The ring that you see there is not made as a ring for some general desire, is because it hosts something that is shaped as a ring. It's a very powerful lamp that can now be used to help us understand and explore what materials are. So we can imagine to go there, and in the enormous density of experiment and material that we can use to this lamp, the lamp that projects light to this white covered block, it's an extremely powerful light and is shielded from all over the direction. Inside, what you can find is something like an extremely powerful digital camera that you can use now to understand and explore each atom inside of a material that you're studying. I have the picture here with my collaborator David to give you an idea of the scale and the sizes. And now we remain with the last challenge is, as I said, how does the electrons move inside? Which is the main question that I had at the beginning, right? Is what makes your computer work, is what makes this device that transport a lot of power over long distance capable to operate. How electricity moves inside the material. This is really something that takes a bit of challenge, but as every project, you can break it down into 3 steps. Into first of all, designing, visualizing what you want to do and create it. This one case when there's a full design of the micro structure that will be created, and what you see next to it is something like a nanometric printer that can allow to do that. Once you have the design and you have your vision, that's a creation. And this is, for example, one of the experiments that I've done. And once you have the creation, follow with the test. And again, the smaller you want to see, the bigger the machine that you have to use. And this machine that you can use is actually the same. It's upper floor on the right and lower floor on the left. It's a magnet. It's just a magnet. Just the one on your fridge, just incredibly more powerful. The power to turn it on at the maximum of its capability is the same as accelerating to high-speed train at maximum speed. And that's now what we can use to explore the quantum properties in these materials. And now with this path, as you can see, it takes a lot of competence, a lot of experience, a lot of knowledge to go there. And what I want to share with you is a bit the lessons that have been learned, which I think are common to creators and innovators. So first of all, you see there's a lot that was necessary to understand, to make us create a vision. And the conclusion is, today is not a time for a lone genius. It probably has never been in recent history. I presented stuff that I've done, but the reality is that it's something that I always had to come with experts to do together. Today, what we see and what I believe is that we deal with so much complexity that you cannot anymore close yourself into your own project and believe that you can achieve the results that you want to have, in particular if you want to have a large-scale impact on your community and people around you. And the next step is, if you want to achieve that, you oftentimes today need interdisciplinary, which means you have to bring together knowledge from different canonical disciplines, right? That's math, that's chemistry, that's art, that's philosophy. But I guess as architects, this is not really necessary. Architecture is interdisciplinary by definition. What I think follow with the first and is the new part is that today we need diversity more than ever. And why interdisciplinary is combining knowledge from different disciplines, and someone can do by itself, right? Architecture is an example. Diversity comes from a need. And the need is that you need different experts, because you as a single person cannot be anymore the expert in all of the aspects of your problem. You cannot keep all the leads of the things that you have to solve. And that puts you in a very specific problem or challenge, I would say, that you need to come together with people that are much different than you to solve a problem. And first of all, you need to step down with your ego to do so, because that means that the other people around you in that table know something that you don't. That's the first step, the first challenge that you have to pass through to achieve that. But that's the only way if we want to get forward in creating and innovating. And I give you just one example that I see of this situation of future challenges. You can see here, this is really one path that we are deciding to take it, in particular in Europe, is going very strong. We want to create new solution for energy. We want to create something, and we end up building in the middle of the sea. That's already a complete different environment. And I want to give you an example again related to energy. First of all, because it's something close to me, and second, because I think it's something that will come very close to all of us for whatever project we will be doing. If we take the example of how we solve the problem of having electricity for everyone, we took a solution that is simple. We built something unique, one location, very powerful, and give energy to everyone. It can work. You can complain that has side impact, but it's simple. You have good control in that. What today's vision as a future is something like this. Now, the challenge here is a lot more complexity, a lot more direction when now you want to have your electricity going, a lot more how the different intertwined of your construction will be, right? Now, if you have your residential complex that charge cars, that's not a simple task. I mean, if you want to fast charge a car, because of course you're used to getting your car refueled very fast, this charging will take as much as 3 households or 10 households if you really have the fast one. So what you're gonna do, you're gonna ask to have enough power to have 1 house and 10 more per every car you want to have. What if every household has a car that will take as 11 households together? And the truth is that, you know, there's not a single person that will have a solution. This only way is to come together and combining our different experience and knowledge to do that. And I just want to close with one example. The main obstacle that we're going to see is complexity. Complexity from the fact that there will not be anymore the opportunity to solve problems with me and others, right? I couldn't anymore imagine that I go until a certain distance in my problem and say, I did my part, from now on, someone else will continue. This has worked in the past, but now, because of this way how problems are intertwined together, it will not be possible anymore. You have to come with an us. You have to come with, we solve problem together. And the image that you see there is not a drawing. It's a trajectory of something very simple, but it can get very complex. It's a trajectory of a double pendulum. If you take a pendulum, a single one, right, it makes a clock work. It's very predictable. If you attach a pendulum to a pendulum, you might imagine it remains simple. It is not. It becomes extremely complicated to predict. And that's indeed, I think, the situation we have for creating when a lot of knowledge comes together. We do have a lot of tools together to solve problems today, but we also have a lot of challenges to use them. And this is, I think, is a good reminder every time I start a project on how simple things can get extremely fast, very complicated. And with this, I want to conclude my experience. And I want to thank you all for your attention. I'm really open for any question and discussion.
Thank you, Eduardo. Right now we will proceed to the Q&A section, if you don't mind. I believe we have here from Mario Medrano. I'll read it to you. On what materials can we apply these methods being useful on architecture? Okay, so you can go ahead and answer that one.
Stop sharing. I think we can continue just with us. On what materials can be applied in architecture, I think, you know, there's no limit for materials to be applied in architecture. Of course, you have your boundary conditions, which is volume, which is cost. So, you know, but there are interesting materials that are applied in architecture. For example, self-cleaning paint is an example where you use nanotechnology, you use electronic properties of materials. So there's countless possibility within the boundary, right? It's the same, it's a tool. So there are tools that will not do the job. They will not do because they're too big or too small or too expensive.
Okay, thank you. We have another one from Claudia Alarcón, and it says, during your preparation in innovation at your master at the MIT bootcamp, did you work closely with architects?
So that experience, I did not have direct work with architects in that specific project. Where I worked with architects was throughout my other master in management of innovation. There was 2 years where we worked with teams of designers or architects from my home university. There typically we would have different projects. We break down the challenge of innovation in different steps and we work one by one, right? There will be social impact. There will be the sustainability of innovation. And that, right, it's independent of the field where you work. So it was very interesting to work alongside architects there because everybody brings a different perspective on the challenge and different, you know, way to start tackling the problem.
Okay, thank you. And then we have a question written in Spanish. I'll read it right after this one.
Yeah.
It says, how long do you think we will reach those changes?
Changes, I think would related to the last slide, probably towards energy, I would imagine. If that is the case, I think it's a never-ending change, right? It's a continuous transformation because continuously we evolve as society. It's a very complicated challenge because you're not reaching for one goal today. You can set your goal today based on your need today, but by the time you reach it, it will change. So you always imagine that you're solving a dynamic problem. You're not solving today problem that will remain the same tomorrow.
Thank you. Well, I would like to thank you, Eduardo, for being here with us and joining us today. And I believe we have another question right now. It says, within architecture, where can we find applied materials such as graphite?
Right. Well, I think you saw that at the beginning, Portlandite is the basic material that constitutes concrete, is extremely similar to graphite. And the way concrete stays together has a lot to do with the properties of graphite in a certain sense, right? Because concrete is this combination of material that remain glued together. Graphite has a lot of application. For architecture itself, not very common, but you use it to draw your first sketch with a pencil. That's graphite.
All right, thank you. And we have another one here from it's from Claudia Alarcón. It says, I'll read it in English. It says, how did oil industry has affected your work, and how can we, as I believe as architects, can push the use of more clean energies?
Sorry, could you repeat? I lost a bit there.
Yeah, it says, has the energy industry affected your job? How can we use more green energies according to your experience?
Right. That's a challenge, as I said, right? It's one question where one expert cannot have a good answer because we need to come together with different experts to come with good answers. Now, I think when you come to these questions, you first need to ask yourself, what is the problem you're solving first, right? Do you want to always maintain the same quality of energy for everyone, which today we give very obvious, but in other countries it wasn't the case. Quality of energy means you plug your computer to charge and it does charge because there's enough energy, or it doesn't blow up because there's too much energy together. You want to have that, then you have to solve for that specific problem. You want to cut carbon emission, then you have to go through another path and say, okay, what produce the most? What I'm seeing now today is really the complexity of the challenge. One has to prioritize and understand what to do. What I'm doing in my job is giving tools to other people to solve this problem.
Thank you, Eduardo. So if there are no more questions, I'll go ahead and proceed with the recognition and with the Veras recognition. So I'm gonna go ahead and share my screen. So it says, Universidad Iberoamericana de Tijuana otorga el presente reconocimiento a Eduardo Martino, PhD, por su excelente charla Lessons Learned from Being a Quantum Architect, impartida en el marco de la Semana de Arquitectura, replanteando el espacio, llevándose a cabo en la modalidad virtual, Tijuana, Baja California, a 1 de noviembre del 2021. And we'll send this recognition to you, Eduardo, and thank you very much for joining us today. If anybody has any more questions, please write them in the chat. Suri, Sergio.
Nada, pues me parece que es muy interesante lo que hoy nos ha presentado Eduardo. De verdad que nos abre a un panorama. Voy a decirlo en español y ahorita Erika lo va a traducir para que nos escuche también nuestro conferencista y para el público que estamos escuchando. Y de verdad que el visualizar todo este trabajo, toda esta investigación nos abre un panorama de replantearnos los materiales con los que estamos trabajando, ¿no? Creo que es indispensable estudiar más, analizar más a partir de esto que nos ha mostrado para poder innovar en las arquitectura, en los materiales de la arquitectura. ¿Quieres traducirlo, por favor, Erika? Para no alargarme mucho.
Sí, claro. Okay, so thank you for the talk, and it's really interesting, like knowing about the materials and the work, right? And visualize the work and rethink the materials we are working with, and to analyze and process all this information, to rethink and in a certain like thought, rethink about new innovations we can work with. And thank you.
Thank you. It was really my pleasure. And I think if I wanted to bring something, was really the possibility to rethink and evaluate, in particular understanding how materials and are tools, and how innovation comes by bringing together tools that are somewhere, right? We live with so much knowledge today that we kind of live in a gigantic workshop where there are tools everywhere, hidden in every corner. Our challenge is to understand where they are, what they do, and how to use them to really bring together and create for what we want to have.
Yeah. ¿Cómo consideras que esta visión de los materiales, qué tan lejos o qué tan cercanos estamos del futuro en donde la arquitectura debe de ya cambiar el material? O sea, ¿estamos avanzados o no? ¿O crees que falta mucho por seguir indagando y analizando a partir de los materiales? Erika.
Okay, how far do you see this change of material or this a process to innovate in new materials? How far are we for changing the way we build and the materials we build with?
Yeah, I think it's very interesting, because what I show is creating the tool. Now, I think in architecture, the game is how to use the tool properly, how to create it the best way. I think a lot that we have to do today is really not only using new materials, but understanding how to use better what we already have. We learned how to build first with stone, then we understood that we could have liquid stone, which is concrete, which is a brilliant material. And then we understood how to combine that with steel to make something stronger. But there we had the pitfall of, you do that incorrectly, you create something that's actually weaker. And being Italian has seen the shortfall of creation of reinforced concrete structure that fall and fail, such as bridges, unfortunately. I think really where we have to focus is take the best also from what we already have. So understand that this might be something new, but what more can we get from what we already have?
Yeah.
Thank you. So it's kind of a constant like looking for new technologies and for new materials, right? It's not like an static investigation. We are always have to search for more.
Yeah.
I think also, you can use the same and additional creativity, additional ingenuity in what you do brings a lot more. And I think, I think that's really the concept that I've seen for the creation with material. You might already have what you need close by, maybe somewhere else, and you just need to reuse it.
Excellent. No more question, Sergio? It's okay, Omar?
Oh,
Okay.
just to say that it's really interesting how to me the not just the application of the material itself, but the process of getting there and the process of understanding all the, you know, as you said it, that we're using nanotechnology like since the beginning of time with the with this glass that you showed us in, I believe it's Milan's cathedral, right? And it's really really interesting how we don't understand the process yet, but yet we're still using the material, right? So the process of getting there and understanding the full potential of materials and the full potential of the technology itself, it's really interesting. And well, just wanted to thank you, Eduardo.
My pleasure to be here.
Pues agradecerle enormemente por estar presente de forma virtual en Tijuana, y esperamos que pronto puedas estar acá en la frontera norte de México, y en donde seguramente nos gustará mucho ver cómo tu trabajo, que esta investigación, todas estas primeras ideas que nos has presentado, que hay un gran estudio, pronto podamos seguir viendo los avances de todo tu trabajo.
Gracias.
Adelante, Omar.
Thank you, Eduardo. And yeah, well, Turi's saying that we hope to see you soon here in Mexico, to see your work, and she's thanking you for being here with us in such a short notice. Thank you.
Thank you very much, guys. It's a great pleasure. Hope you will have a great week also of discussion. I think you have a lot of interesting talks ahead, and looking forward to be in Mexico soon. As I said, January we'll be there.
I hope.
With pleasure.
Yeah. ¿Dónde podemos seguir su trabajo?
She's asking me where can we follow your job?
Good. So my current job being mostly now focused with now industry, it's not much accessible, but whatever will be, you will find, of course, on my LinkedIn. You can find me in Eduardo Martino, and from there basically is where I can take care of either publication or presentation. I do try to keep a relatively active social media presence where I want to distill things that I have. I think also Sergio added the link for that presence. I have one presentation on YouTube. You can find it with my name, and there's one link from Instagram. I can add it to the chat, maybe. You can add it. There is more distilled work, right? So you will see like a different perspective of what I do. I add it here.
Perfect. All right. Is the Instagram? Okay, Sciences Apparel. Okay.
Yeah.
Thank you.
Yeah, they follow the concept of, whenever you discuss science, there's an apéro, it's the Italian or French way. When, you sit together, you discuss with a drink of a beer and a cocktail.
Excellent. I think that there is one question more.
I think we have one last question. It says, what is architecture for you? To live in a general concept.
So I think nice understood that there are categories for a lot of situation, and architecture it's a path of innovation, and it's the path of innovation for a problem. Innovation is always a solution of a problem, and architecture is first of all the challenge of transforming our way of living as a social being in a solid object that is both a way of representing ourselves and a functional entity.
Thank you.
Great reflection. Is very different. The significado de la arquitectura, ¿no? All right, it's okay. creo que terminamos, Omar, para poder ya concluir. Agradecemos nuevamente y agradecemos a quienes nos están viendo en vivo.
Okay, well, thank you again for being here. And thank you for everyone watching the live stream in Facebook. We'll give an end to this amazing talk. And thank you, Eduardo, again for being here. So, and thank you all for being here too.
Thank you very much. Thank you everybody for following. Pleasure.